who will be talking, whose talk is titled Dennis Saves the Day.
That work? Oh, yeah. Sure. Well, it's certainly nice to be here. I'm going to give this talk by chalk, which we'll see how that works. I used to be able to do it well, but modern technology maybe defines well, gives a new definition of well. I met Dennis in 1968 when I came here to chair the Stony Brook department and try to hire a bunch of people. And Dennis was right at the top of the list. But I failed. He made a big mistake. He subsequently went in the era of his former ways and eventually came, and which is terrific. Through no fault of his, about 10 years later, 9 years later, I stopped doing mathematics, started doing something else. But it was always sort of running around in the back of my head, but I wasn't doing it. But in 2004, for one reason or another, I started thinking about a problem that I had actually thought about off and on to no particular avail for a long time. And then I seemed to be making some progress in it, and I more or less went back to doing mathematics. And it turned out I collaborated with Dennis. And I'll give you that a little background. A little background on that. And so I have some charts. So in the early 70s, I worked with Chern, and we did some things. Is this visible? Yeah, so it must be. Anyway, we did some things with principal G bundles with connection over a manifold M. The connection is theta. And omega is the curvature. Yeah. And P is an invariant polynomial. On the Lie algebra. On the Lie algebra. Just have to remember that. And so if I take the curvature, suppose it's dimension, suppose it's degree D, and I take the curvature and I plug it into the polynomial, you get a closed 2 form, closed 2L form. Downstairs on M, and its cohomology is independent of the connection. So this is, of course, the famous Chern-Weil homomorphism from the ring of such invariant polynomials down to the base of M. They represent real characteristic classes, etc., etc. Now, if you lift the form, if you lift P back up to E, it becomes exact. So, here, let me give this as a name. We'll call this pi. This is the softest chalk with which I've ever worked. So, either I've gotten stronger in my years, or the chalk has deteriorated. But So upstairs, of course, you lift the principal bundle up over to itself. The bundle is trivial, so any characteristic class vanishes, and therefore if I lift this form up, it will become exact. So if I look at pi star, pick that up, of p of omega to the L, that's equal to, that's exact, so it's the differential of what's called TP theta. And that's where, okay, so, and this TP theta is well defined up to exact. Up to something exact. So, of course, you could write a formula down for it, but there are other formulas you could write down. But if it's going to be functorial, if it's going to, in this category of topological connection and so on, just always pull back to the, to do this job, so that this makes this exact, then the choices are limited to a family which is defined only up to exact. But that's just fine. Now, with Chern, we found many uses, or anyway, some uses for these forms. Already? Of course.
Well, it's just, are these TPs what they call the Chern-Simons forms?
Well, yes, I suppose. They are. But
TP stand for Chern-Simons.
T for Chern, and P for science. Chern didn't know the alphabet very well. I mean, he wasn't born in this country and so on. So, this was good, but it would be nice, these forms are up there and the manifold's down here, and it would really have been nice to get something downstairs. Now, there wasn't going to be any form that you get downstairs, except for the original P of omega to the L there, that characteristic form. But there was something. So you can do the following. You can define, now this is S. We've got an S here, see? So, okay, let's see. So I want to have so suppose that P of omega to the L represents a universal integral class. Integral class, let's say, in the classifying space of BG or something. So, suppose that. Like, suppose it's a Chern class or a Pontryagin class or whatever. Then,
Jim?
yeah.
You mean the image of the integral and the real, right?
Yeah.
That's what you mean by represent, right?
Yeah. It comes from it. It's associated to it. The polynomial exists. The polynomial exists on the group that has nothing to do with this particular situation. So you can always do this, and you can do it back in the classifying space, with the connection on the bundle, and you'd get, I'm assuming, an integral class. That's right. I mean the real image of an integral class. Universal real image. So you copy there. Real image. an integral class. So then if I pick one, pick such an integral class, mu, then I can define what we call SP sub mu of theta, and this is an element downstairs in homomorphisms from 2L minus 1 odd cycles, 2L minus 1 cycles in M, let's say singular cycles, into R mod Z. And moreover, this element, this map from cycles into the circle, let's say, has the property that if it's acting on a boundary, so S P sub mu of the boundary of Y is just the integral over Y of this P of omega L modulo the integers. Okay, so these are things, and they're natural. It turns out you can do all that, and there they are. So they're functions from cycles to the circle, but if that cycle is a boundary, it's nothing but the integral of this form over the interior modulo the integers. And that's well-defined, these are well-defined, and all the rest. So, okay. So, this was interesting. And so I'll give you one example. So, suppose the group is the SO2, and you have E going down to N. It's an SO2 bundle with connection, and little chi is the integral Euler class. And P is the Pfaffian polynomial. Well, P is just a curvature factor, so we'll just put it this way. P sub chi, the polynomial associated to that, is the form associated. Is just 1 over 2 pi times the curvature. Okay? Everyone knows if you integrate the curvature, this thing, you'll get the Euler characteristic of that bundle. So now I want to say, what is SP? So if I have a closed curve downstairs, which we'll think of as a one-dimensional cycle, then SP chi, called as gamma, SP chi gamma is nothing but 1 over 2 pi times the angle of holonomial. And this can be extended to all cycles. It doesn't have to be just a closed curve, but any one-dimensional cycle. So holonomial around the cycle reduced, turned into something between 0 and 1, R mod Z. Holonomial on the cycle is the most elementary of these SP things. Okay, so now we go over to this board here. So, I don't know, is Cheater here today? He promised me he wouldn't attend this talk, and he kept his promise. But, so he and I started talking about this stuff, and we decided to make a definition. So with Cheeger, we made a definition. Differential characters. Now we're in the smooth category, we've got manifolds and all that. And so, and it's a graded, so we're going to define this graded function. H hat up a k of m, so manifold downstairs, equals a set of elements in hom, cycles of 1 degree lower, z k minus 1 of m into r mod z, such that, with the property, that f of a boundary of y will be equal to the integral over y of some form, which I'm just going to call omega sub f of y, mod z. Okay. So this just generalizes that notion and gives it a fancy name, differential character. So it's all homomorphisms from cycles into the circle, into R mod z, which on a boundary is just the integral of some form over its interior. Now,
so in particular, differential forms are things.
a differential form, absolutely. I'll give a couple of examples. That's obviously one. But let me just say a couple of things about this before we do that. So it's easy to show the following. One, omega sub f, did I call it? Oh well. I don't know, should I? I'll go back and call it capital letters. Okay. Omega sub f is closed. It has integral periods. And it's unique. So the definition does not seem to require that this be closed with integral periods, but anything will be easy enough to see that if you really had such a differential character, it would force this form to be closed, have integral periods, and be unique. Now, the second point, I'll simply say that associated, to f is mu sub f contained in hk of mz. And it has the property that the Durham image, let's see, what was that? Yeah, the Durham image of omega sub f equals the real image of mu sub f. Now this is a fairly simple construction, which I won't go into. But nonetheless, there it is. So you have a differential character. To it is associated a closed form with integral periods, omega sub f, and an integral class whose real image is represented by that form. So this sort of modest definition already comes with a few, with a little juice to it. Now, this is the only board that moves, I suppose. Well, okay. I'm gonna. Yeah, I didn't want to go so far to the left.
No, behind that. It's too deep. It's too deep.
It's too deep? Yeah. I'll be a son of a gun. Oh. Hey, that's very exciting. How many boards are there here? 4? This is very funny. exciting. I'll take advantage of it. Okay, so let's have some simple examples. So, of course, as the gentleman said, let's make one piece of definition. Wedge k minus 1 sub z equals closed with integral periods. That's the definition for any k. I just happen to pick that one. So that means closed form with integral periods. So now, suppose I have some form that's contained in ordinary wedge k, k minus 1, just any k minus 1 form, but I'll take it modulo this ambiguity, wedge k minus 1z. Call that theta. And in fact, I'm going to call it an equivalence class, see, because this is quotient space. Then I can, if A is a cycle, and A is contained in Z, k minus 1, I can define this thing evaluated on A as the gentleman said, simply the integral over A of theta mod Z. So this whole thing naturally, sort of trivially sits inside differential characters. Obviously, if I integrated this over the boundary of something, Stokes' theorem says, oh, well, that's the integral of d of theta in the interior. The ambiguity washes out because these are closed forms. And so for this particular guy, omega sub this thing is just an exact form, namely d theta. Okay? Another thing that sits inside it, very simply, is the R mod Z cohomology. So if I looked at hk minus 1 of m R mod Z, that's just actually equal to, or isomorphic, naturally, to Hom, well, it's not, yeah, it's Hom of cycles, zk minus 1 to R mod Z, such that the restriction to the boundaries, b k minus 1 equals 0. So it's homomorphism from cycles into the circle that just vanish on all boundary elements of the boundaries, and so obviously that's one of these guys. Well, okay, now I'm gonna put up something that I'm gonna want to leave here. Now I'm out of boards. Let's see. For some reason I picked this side as being the best side. No, maybe I'll stay with this side.
Pull down the middle board,
Yeah.
behind that board, and then the middle one.
You're not telling me I have a...
Over here.
What can I do?
You have one back one down and pull back right there.
Yeah.
And then put it
I was planning to exhaust this set until I ran out of board. I'd go back. This is okay, because I'm going to just leave. I'm going to put up something that I'm never going to take away. I'm never going to take away. So now I want to fit this gadget, this thing, into some exact sequences. And into some exact sequences. So we see where this fits in the galaxy of all previously known functors. See, we put it a few. Okay, so we'll put it in the middle. H hat of a k of m. And down here, because of that form, I have wedge k z of m. It maps into this because that's the standard form. And I already told you it goes up to hk of mz. It goes up there. And these both come down to hk of mr. And this little piece commutes. All right? Now, I also told you that
When did you tell us it goes up into H, K, and Z?
right up here, associated to F is mu sub F in hk of mz. See, I told you. I told you.
That's the definition.
Yeah, that, I mean, that diagram is, 2 is a sentence of that.
2 is a sentence of that diagram. That's exactly correct. This guy is very helpful. Okay. Now, what is your name?
I'm Nathaniel.
Nathaniel. Okay. You have a nickname, Nat? I'm calling Nat or
Nate.
Nate, okay. So, as Nate reminded us, hastened to remind us, these forms with integral, forms modulo those with integral. There's a wedge k minus 1, mod wedge k minus 1, z is in this thing. And as a matter of fact, it's an injection. And now I'm going to give these, well, this is an injection. And finally, as I pointed out, that hk minus 1 of m r mod z is in this thing. Okay. And over here, we finally have hk minus 1 of mr, and that goes in here by reduced mod z, and it goes over here by theorem. Now I'm going to put in some more maps. I'm going to give these things some names. I won't put any more maps. We're going to call this map delta 1. And we're going to call this map delta 2. And we're going to call this map I2. And we're going to call this map I1. Now, this doesn't need a name. Real goes to R mod Z. We know what that is. This is a theorem operation. Real cohomology goes into closed forms, modulo those with integral periods. And this, of course, is just putting something into, you know, with real, just making tensoring with R. And this commutes. It's not completely obvious, but if you work it out, it is obvious. It becomes obvious. Now, if you go from R mod Z into here, and you come up there, that's a map from here to here. You follow this along, and that turns out to be the box star. Well, actually, it's the negative of the box star, because of the way some of this was defined. Now, here's forms. You go up to there and down to here, and forms of 1 more degree. And this turns out to be simply exterior differentiation, D. And finally, the diagonal sequences are exact. So I got a 0 over here goes in here, and a 0 up here that goes up there. And this goes down to 0, because that's onto. And this goes in. So, now I'm not going to, some of these things are obvious, and some are less obvious. For example, that that you hit every element in integral cohomology is not so clear, but you do. If you hit every element in here is not so clear, but you do. In fact, from the diagram, one can see you simultaneously hit every pair as long as they coordinate, as long as they represent the same thing when you go into real cohomology. And so this functor, which is kind of nice, simply defined, fits into this diagram of all these familiar functors. And It's natural if you take a C-infinity map from one manifold to another and you pull all this stuff back, everything in sight will commute. And we're going to call this thing the character diagram. I thought I'd have a place to write it above, but I'm going to have to write it here. Boy, character diagram. I'll just call it the diagram. It's the only one I'm going to have. Diagram. D-R-A-M. Okay, diagram. Oh, I forgot. No, that's spelled right. Okay. So, now, Jeff Cheever and I did this made this stuff up. Boy, it looks awful, my little diagram. Can you all remember that this is... I figured you could remember that. This turned out to have some very nice uses. It gave some simpler proofs of the things that Chern and I had done with these TP forms. The Weil homomorphism factors through this thing, so that, and that's sort of what that S stuff showed. So if you have a pair now of an invariant polynomial and an integral class that represents whose real image is that pair, this SPU, is a differential character, and it lifts the Weil homomorphism through this. When it gets down to here, it's back to what it originally was, and there's a little more to it because it comes up here. But even if both of these maps are 0, there is a simultaneous kernel, which is practically this. But it's this modulo, it's a torus. It's this modulo the image of the integral cohomology. So this thing here is not determined simply by these two sides. Okay? Nor is it simply the sum of the images of these two guys. It's more, so otherwise it wouldn't be so interesting. So the kernel of the simultaneous delta 1 and delta 2 is simply the torus of the real torus of the dimension, the k minus first Beatty number of the manifold. So I'm just telling you that. There it is, and it's good for some things. Now, in around 2003, is Blaine Lawson here? Ah, another guy who promised not to come, who kept his promise. So Blaine Lawson, along with, I think it's Reese Harvey, and a guy named Zweck. Maybe Zweck is here. Is Zweck here? I never met Zweck. I'm looking forward to meeting him, but he's not here. Anyway, they came up with a lot of other constructions that turned out to be isomorphic as functors. What do you call it? Naturally, what's the equivalent? Equivalent to this functor. They come up with graded functors. They constructed some of them in similar ways, some of them in somewhat different ways. And in each case, they proved that this functor was equivalent to differential characters. Well, it occurred to me, seeing that paper, I think that's one of the things that sort of inspired me to go back to doing a little bit of mathematics, that maybe the diagram itself characterizes the functor. In other words, any time you have any functor that satisfies the diagram, it's this. There's nothing else to do it. Nothing else to do it. Now, it's not such a crazy thought, because this is a very tight set of conditions. I mean, it's sort of trapped in here. And how many different guys could you really come up with which you could come, whatever. I like to keep my grammar good. Are there things up with which you could come that would satisfy this? It's not so easy. And it turns out it's true. It's true. This diagram does characterize this one, and that's what we're going to sketch here. And that's really where Dennis comes in. Now, today, this is an example of what's called differential cohomology, which a lot of you have undoubtedly heard of. This is ordinary differential cohomology, or just plain old ordinary differential cohomology. And it's called ordinary because it is associated with ordinary cohomology. So why not ordinary differential cohomology? There are similar diagrams one could draw and exist, and functors that make sense, for, I think, perhaps any of the extraordinary cohomologies. Singer and Hawkins wrote a paper on this showing you could always construct functors like this, and they would satisfy diagrams more or less like this. So, so this was the first example of this, and I forgot to mention, completely independently of Jeff and I concocting this thing, Deligne was making up Deligne cohomology. And from a wholly different point of view, and not thinking so much in the real category, I think in the homomorphic. I don't know much about Deligne cohomology, but it wasn't so the smooth manifolds, particularly. That wasn't his focus. On the other hand, if you do Deligne cohomology in the smooth category, it's a functor and it's isomorphic to that. So, and that was in the same time frame, in the early 70s. So there was something in the air that made one want to come up with things like this. So this is a model. Differential characters thus are a model for ordinary differential cohomology. And it turns out, in the ordinary case, there's only one. So that's what we'll talk about briefly today. So, I had an idea of how to prove that.
Sorry?
Yeah.
In the non-ordinary case, it's not unique?
Yes and no. In even K theory, in the even case, it is unique. And that was very recently proved. In fact, Andrew sitting up there had a little help along with a couple of Germans. Bunke and Schick. You guys know Bunke and Schick. So they proved that. In the odd case, the diagram is not enough, I believe, to characterize it. You need something else. In fact, maybe it's pretty much always unique if it satisfies a push forward, some kind of push forward condition. I think that was Andrew's thesis. So, so the answer is almost yes, but you need the diagram alone does not always do it. The diagram alone doesn't always do it. I mean, exotic cohomology can be very exotic. I mean, it's not, you know, I had never heard of extraordinary cohomology when I came back to doing mathematics. I mean, I guess I'd heard of K-theory. I knew, oh, K-theory, but I didn't realize it was dignified with the name of extraordinary cohomology. I learned a lot since I came back, but not nearly enough to make up for 27 years, but I've learned something. And but some of these cohomologies are very weird. Like, one thing that's weird about extraordinary cohomology, that in general, Hom of homology into R mod Z is not R mod Z cohomology. And you might think, well, why not? I mean, after all, what else could it be? But it isn't, in general. It is, however, in K theory, as Dennis has told me by a miracle, there's a miracle that goes on, that certain of the more standard extraordinary cohomology theories have this, the fact that the Pontryagin dual of homology is cohomology. It always should be that way, in my opinion, but my opinion doesn't count for heck of a lot. So I had an idea of how to prove this theorem, this uniqueness theorem, and I came to Dennis. Well, first I went to Jeff. First I went to Jeff Chern and said, I got this idea. Here was the idea. I'll tell you the idea. After all, it's a functor, so it's supposed to be natural. So one thing you could do is say, okay, if I have some fake functor, something else that fits in, I want to get a mapping of it into HK. So suppose I have some imposter, some other thing that satisfies this diagram. I say, okay, how do I get a homomorphism, a natural transformation which takes it into this? I had this great idea. I said, okay, I need a function on cycles. Okay, I know what I'll do. I'll take a cycle and represent it by a manifold, a lower dimensional manifold that I just push in. So I can say, I'll just immerse some oriented manifold whose top class, this fundamental class, is homologous to the cycle. And then I'll just use this, well, anyway, it was an approach. And I told Jeff, hey, I got this idea of how to do this. You do that, then you evaluate the obvious thing on the cycle. You get an R mod Z number, and that must be a homomorphism with this, and everything was Jake. And Jeff said, well, I don't know. You better talk to Dennis. He knows about things like that. He knows about things like that. Things like that being, can all homology classes be represented by, let's say, immersed or just sticking manifolds in? And I was actually just sitting quietly in my office, and he walked in, Dennis, to ask me some question, not knowing that I was going to come back to him with a question. He had some question about, I don't know what, but it wasn't mathematics, whatever. I said, while you're here, tell me this. Can every homology class be represented by a manifold stuck in? And he said, well, no. He was very clear on that point. No. But it's a good try. He said, it's a good try. Poincaré asked that question. It's sort of an obvious question, right? We got homology theory. Well, why can't you realize if I just stick it in some other manifold? So it's not completely stupid to ask that question. I think Poincaré asked that question, and he came up with the same answer that Dennis did. No, can't. You could do it with a multiple. So you had a cycle or a homology class, some multiple of it could always be represented by an immersed or whatever, a stuck-in manifold. I don't know. You don't need an immersion, right? We just stick it in there. Look at the image of its fundamental class. So, in a sense, the Q, if you were only doing homology over Q, then you're all set. Then you can get every rational homology class by now. But you cannot get every integral class. And I was bound to get the integral classes. So, looking at so that was the end of my theory of how to prove this theorem. But Dennis got kind of interested in the problem. And so we started, he said, well, maybe there's another way, maybe. So maybe there's something else we could do. And we did. To a large extent, he did. But I sort of hung around. So, and kibitzed. So I'm going to make a couple of definitions here, and then I'm going to outline how this proof actually goes, what the right homomorphism is, and what the three facts in topology. So there are three facts, topological facts, which Dennis either recalled or invented or both during the course of our discussions. Based on those facts, one can prove this uniqueness theorem. And they're really very pretty facts, but I'd never heard of any of them. So, and I don't know if anyone else had, but I suppose perhaps someone had. So, but first let me state now what, put something formal here on for you. How's time? What time is it? What?
You have about 15 minutes.
I have 15 minutes, so
The
let's,
other side of the eraser works better.
what?
The other side of the eraser works better. Yeah, bizarre.
Nate, why didn't you tell me that? Okay, well, that's true, that's true. All right, so let's make a definition. A character functor is a 5-tuple G hat. I'll put up star because it's going to be graded. G hat, I1, I2, delta 1, and delta 2. A functor into abelian groups. Now it's an abelian group valued functor. It's a 5-tuple of all this stuff, which satisfy, and these are natural transformations and so on, which satisfies, it will be clear, which satisfies the diagram. Okay, so that's a character functor, right? It looks just like the other one, except it's called G. Okay, that's the only difference. Now, here's the theorem. Any character function spell very well. Any character function is equivalent to H hat. I won't put an S triple, I quintuple. The H hat star via a unique natural transformation. Commuting, we'll call it phi. Which commutes with the identity map on the other 4 functors. So in other words, you take an element in G star, you map it over to the H star, and then go by delta 1. That's the same as first going by delta 1 over here, and you get to the same place. So if you take something over here, and you stick it into G, and then go over to H, you might just as well have stuck it into H in the first place. So it's as good as it gets, and it's unique. There's only one. So that's the theorem. So I'm going to sketch how this gets proved. And so we need a Dennis definition. So this? Okay. Okay. So we'll make a definition. An open U contained in M is called K good. If H L of MZ of UZ, the interval cohomology, equals 0 for L greater than K. Okay, call that K good. You ever hear that definition? No one heard that. So that he even invented the definition. Okay, there's a definition. So now here is a fact, fact 1. So there's 3 facts. Fact 1.
What's it got to do with M?
U is an open set in M. What do you mean?
What's just an open set?
What's an open set?
Right, so what of M, I guess.
Why did I mention M? Well, I just, usually open sets exist in some topological space, so you don't just walk around with an open set. Yeah, an open set somewhere, it's open there, open in M. It's okay, I've said silly things. So, it says here that, yeah, so any neighborhood, just straight, of the image of a smooth singular, well, so we'll work with here, K-chain, contains a K-good subneighborhood. See? So, this is not a shocking statement. On the other hand, it isn't very, it's not so easy to prove, as it turns out. So, you might think, well, I mean, this thing only had K dimensions in the first place, it was a K chain, why can't you just sort of just thicken it a little bit, and then you think, oh yeah, now I've thickened it, and I haven't added anything particularly to it, so it's the higher homology, cohomology, ought to all go away, but it is not as simple as what I just said. In any event, it's a good fact, so that's fact 1. In fact, I think, I keep calling names, is Chris Bishop here? Is he? He's not here either. Another guy probably. I think Chris helped Dennis a little bit with that group. It's technical. It's not simple, but there it is. It's a great fact. Okay.
The subneighborhood of the singular K-chain.
Say it again.
It's the subneighborhood
Of the
the singular K-chain.
That's right. You take a so here's the cycle. I mean, it doesn't have to be a cycle. Anyway, here's a chain, and it has some neighborhood, some neighborhood, and this chain is K-dimensional. And inside there, you can find a K-good neighborhood. So as small as you want. So you can hug it as tight, no matter how tight you want to hug it, you can hug it even tighter with something that's K-good. So it's just a little smushing. Just a little smushing makes it K-good. Now, so with that in mind, I'm going to define the right map of, I think I'll go up here. I like working a little higher. I'm going to define the right map, phi, from the imposter characters into H hat. Dennis walked out, I think.
That's what he's going to say today.
He's going to save the day, well. No, he walked out. Did I say anything to make him walk out? So here's what we do. So now I want to map phi from G hat, call it K, to H hat. Okay. So now we'll take a cycle. Let me skip my notation. Right. So I'll take a little cycle in here, A, contained in Z, K minus 1. Of M. Cycles. And I'll take U, a K minus 1 good neighborhood. Of the support of A. Okay. And now, I'll let the inclusion, we'll call the inclusion map lambda. So lambda is just going to take this U right into M. It's the inclusion map. M. So since everything is natural, I can look at if I have G in G hat, K, I can look at lambda star of G. I can just pull it by restriction to here. It's not a function or anything like that, but there it is. I restrict it to here. Lambda star of G. Contained contained in, contained in G hat of U. Okay. But now U is K good, K minus 1 good. So we look over here, and HK of U is 0. HK of U is 0 because it's K minus 1 good. So anything above K minus 1. And that means that, and remember now, think of G as sitting here. That thing really came from something over here. It's really a form. It's one of Nate's favorite characters. It's just a form. So lambda star of G is contained in wedge K minus 1 mod wedge K minus 1 Z of U. And I can simply say, okay, phi of G of A is just equal to the integral over A of this. Oh, so phi of G, so it's some element in there, we'll just call that theta twiddle. Okay, that's its name, phi of G. Theta twiddle. G of A equals the integral over A of theta mod Z. Okay? Now, all the naturality conspires to show that this was independent of my choice of U, and it was independent of my choice of theta. Now, if I picked any other theta in here, I'm integrating, it doesn't matter, of course, because it would differ by something. This is a cycle, and that the difference would be integral, so mod Z. So, but suppose I had picked a different U. Well, their intersection would be an open set, would still be a neighborhood of the cycle, and inside that intersection, I could find something K good. So now I have something K good, and by naturality, everything would restrict down to there, the integration would take place inside there. So naturality would save us, and it's completely independent of the choice of u. So this is a good definition. This is a good definition. Okay, well, now, so, but now, so, and it's also, it's pretty easy, to show that this is going to be a homomorphism. No, yes, again, a backwards part. So, our phi hat, our phi, capital Phi, so far has mapped GK hat into hom ZK of M to hom on Z. But that's not enough, because we have to show it's a character. In other words, we have to show what it does on boundaries. So we need to show that if A, or A over here, was equal to the boundary of some E, then phi of G of A should equal the integral over the interior E now of delta 1 of G mod Z. That's what we need to show. See? That way, now, it's really a character, and not only that, it would be using, this would be the right form to integrate over the interior. Remember, delta 1 is this map which gives the closed form with integral periods that we might have started with, or started thinking about. So I have to show that. And this, so, I want to, I think I'll go with this. Now, I want to keep a one picture up here. And I'm going to try to finish quickly because I'm running out of time. I had told Herschel this talk would be only half an hour.
I was just going to tell you.
I know. Well, okay. All right. So now I started with A thing, the cycle. This is A, and now it has an interior. You know, we're making it a boundary, and this in here is little e. Okay. So now here's the next fact 2. Fact 2 is a wonderful fact. So assume dimension M is less than, is greater than or equal to K. Now if, then a smooth singular, no, it's not an M, it's an M, suppose then a smooth singular cycle is homologous in every neighborhood of its image to the fundamental cycle of a pseudo-manifold. guess,
Is it K
an
cycle?
embedded.
Singular K cycle?
What?
A singular K cycle?
Singular K cycle, yes.
Okay.
Sorry. Thank you. Of an embedded pseudomanifold. So, pseudomanifold is, well, every manifold is a pseudomanifold, but not every pseudomanifold is a manifold because they're allowed to have singularities. So, the top dimensional simplices, or if you're going to triangulate, they all, every next to top dimensional simplex is the side of exactly two top dimensional ones. It's kind of like a manifold, but it isn't. It's more general. It can have singularities. And this is the level of generality of objects which do represent homology. So remember, at first I said, let's just take a smooth manifold and hope it will represent all the homology inside, and we could always do it that way. Well, you can't, but you can do it with one of these things. And not only that, I mean, you only have to move a teeny bit, right? So you have this, no matter what the neighborhood that you pick of this cycle, a little inside there is a homologous embedded pseudomanifold whose fundamental cycle is homologous. So that's a terrific fact. And so now, going over here, now I say, okay, here's A, my cycle, and here I'll draw this very attractively compared to a cycle. This is a pseudomanifold, P, and a homology now between these two things. I'm not much of a drawer. And a homology there. And I think I may have already wanted something else. Oh yeah, and the name of that homology is B. Okay, so here's a homology B. A is this cycle, there's its interior because it's a boundary, and here's P. And now, and this B and P and E are all in use. So B, P, B, and A. P, B, and A P, B, and A. Where's Y here? Oh yeah, P, B, and A are all contained in this K-good neighborhood U. Okay, so all this is taking place in a really small thing. You're just perturbing this a teeny bit with this homology, and I get this guy here. So now, here is fact, Dennis's fact 3. Okay, I'll just write it down here too. I'll erase this one, write it down. And then we'll just talk our way through the end about what we're going to do. And this is also a butte. This is fact 3. If the fundamental cycle of embedded P pseudomanifold, if the fundamental cycle is a boundary, then it is also a boundary. In some K minus 1 good. This fundamental cycle, this is K minus 1 dimensions, is some K minus 1 good neighborhood of P. Okay, now, so it's really saying, okay, if this is already a boundary somewhere, and notice the way I've drawn the picture, P is already a boundary somewhere, because it's homologous to A, and A is a boundary, so it's a boundary. It's homologous, you know, it's a boundary. But I don't like this E here. It's too far away, maybe. So I can make it bound in something else, in a K good, another K good neighborhood. We'll call that Y. And now I have Y, and again, P is contained in another K good neighborhood U prime. Okay?
Did you switch from K minus 1 to K minus 1?
I didn't. I kept saying K, but I've been right K minus 1. So I'm half right. Yeah, K minus 1. So now equipped with this, you sort of inch your way along in 2 steps to prove what we needed to prove. And I'm not going to go, I mean, I could, here, well, I'll just say this. It's kind of pretty. I mean, P, so P is a boundary in 2 ways, and I'll just write all this down. So, you go through some calculations and so on and so forth, and the algebra, and then you conclude that phi of G of A is actually, and it's all naturality, so is equal to the integral over E of lambda 1 of G, which is what I wanted. This is all mod Z, plus the integral over B plus Y minus E of lambda 1 of G mod Z. Okay, now how did I get here? You chase around this thing, and you get here, you use naturality, whatever seems natural. And that works out, and you get to this point here, which is splendid, because lambda 1 of G is one of these things with integral periods, and B plus Y minus E, as we will see, B is in the middle, Y and E are the end caps of this thing I've drawn. And so, it's a cycle. I mean, right, this is the opposite orientation of something. It's all a cycle, and I'm integrating this over a cycle, so it goes away. So, the trick was that this last fact 3, I presume, you really need that it's a pseudo manifold in order to get this kind of a K minus 1 good neighborhood of its whole homology to 0, right? So that's where we used the pseudo manifold. If it didn't have we didn't need that property, we wouldn't have needed it, but we did. So you inch your way along, you make P a boundary in 2 different ways, you use 2 different K good neighborhoods, and you have this. And now, therefore, this phi is a natural transformation from G to H. And then the rest of the proof is mostly algebra, chasing around the diagrams, using a few other things which I don't have time to mention, and at the end using the 5 lemma, the famous 5 lemma, and you get the theorem. And now we worked. We kept getting stuck, and then first Dennis came up with fact 1, And then we worked along, and then we kind of got stuck again, and then he came up with fact 2. And then we worked along, and then came up with fact 3. And put them all together. So he saved the day 3 times, as far as I know. And that's the end of my talk.
So I'm afraid that the shuttle is maybe already waiting outside, but I think we still have time for 1 or 2 quick questions. So, yes.
So is when you try to imitate this for exotic cohomology, it doesn't work. Is the essential problem that won't have these good neighborhoods, you can have high cohomology and...
No, I think first of all, the essential problem is getting a good model. The model that we've been working with, although I think we have a different one now, we'll make this much simpler. But the model is vector bundles with connection and equivalence classes and those. It's starting from a very different point of view. And in fact, from that point of view, isomorphism is not as easy as it might be. There's another point of view. So it's just different.
Sir, basic question. On the diagram, it starts with hk minus 1 of mr, and it ends with hk of mr. So,
Yeah.
I think that seems natural is to put another diagram on its right and then
Yeah, sure. It just keeps percolating along.
Okay. And is there any good sense in the vector from h hat k to the h hat k minus
Plus
k,
1?
plus 1?
No. Yeah, because everything gets killed by the time you go around a few of these things. Everything dies. So you can't do it. Yeah, the exact sequence. Both these outside sequences are exact. The Bach-Stein sequence is along exact sequence, and this sequence is along exact sequence. And as you know, if you stay on the train too long on a long exact sequence, you get killed. You get off when the getting is good. Any other questions?
Could get some sense of the theorem. So what is codimension of the singular set in the theorem?
What's the codimension of the singular set? Yeah, I was going to say I think it's at least 2. You can't have. Well, Dennis is a better answer than I, but as far as I can see, you can't have a lot of n-1 simplices folding around an axis, but you can have them coming in pointing. So I think, is that right? Yeah.
Take 2 tetrahedra touching it.
Yeah, that's the archetypical example. 2 tetrahedra touching at a point, but not at an edge, because those edges are supposed to be. There are supposed to be exactly 2, in this case, faces that would come in on that edge. But, of course, an edge was a higher dimensional thing, then you could have the faces. So that's the essential singular set. But I'm definitely not an expert on pseudomanifolds.
But is the only thing you need to know about singularity, so there is some oversets?
Dennis, what's the answer? Is that the main thing you need to know about the singularities, that they have to be codimension too?
Yes.
He said yes.